So in order to move forward, we need to actually move backwards a little bit. That is to say, in order for us to talk about power series, we need to first discuss series. In order for us to talk about series, we need to first talk about sequences. So this is a lesson that is largely review in regards to sequences, and something that you could probably do as a self-study, but I did want to highlight a couple of key features of sequences and some other concepts that will be related and really important to our study of calculus. So first off, what is a sequence? A sequence is simply just a list of numbers in a defined order. We may not know what that order is, but there is some order to it. And we can think about sequences using a number of different variables. So for example, this sequence that we have listed out here, we would say that a sub 1, this is our first term, a sub 2 is our second term, and so on. These little dots that you see here indicate that that sequence is infinite, meaning it is unbound. There will continue to be an infinite number of terms. And a sub n just represents the term in some nth position that we are just unaware of, right? But just representing some general nth position. So one of the key ideas in pre-calculus that we discussed, or that you should have discussed, was the idea of using or thinking of sequences as a function that maps the positive integers to some output in the sequence. So for example, if you can think of f of x 3 over x plus 1, and rewriting this in the way that we would think about a sequence, just saying, okay, when n is equal to 1, what is the value there? Well, when n is equal to 1, we get 3 halves. When n is equal to 2, we get 1. When n is equal to 3, and so on and so forth, and we're seeing the outputs of a function in a particular sequence. So now that we have that, one other thing that we also need to discuss are the idea of factorials. So factorials are a really important part of the curriculum, and they're going to show up in calculus in a number of ways, really kind of just organically, which are kind of cool, but we'll get there. But the idea of factorials really just being the idea of taking the power rule multiple times in a row. So n factorial would be that value n times its previous number, n minus 1, times that previous number, n minus 2, and so on until you get all the way down to 1. Okay. Also, it's worth discussing real quickly the idea of recursive sequences. And those are simply sequences whose terms are defined by the previous terms or the terms that precede them. And the most famous example of this being the Fibonacci sequence, right? And there's a lot of really cool videos out there on Fibonacci sequences and how they relate to naturally occurring phenomenon, which I won't discuss too much right now, but definitely worth a look if you're interested. So let's just do a couple of practice problems here just to get us familiar and refamiliarized with the idea of sequences and some notation things that we should be aware of. So let's take a look at this first one where we have to simplify n plus 1 factorial over n minus 3 factorial. Well, what's going on here in the numerator? Well, this idea is that we have n plus 1, and we're multiplying n plus 1 by all of its previous terms. And at first, this would seem kind of unwieldy because we don't know what n is. So at first, it may seem like we have an infinite number of terms that we need to multiply. But if we really kind of think about this for a second, we got n plus 1. What would the previous term be? Previous term would then just be n plus 1 minus 1, which is just n. And then that previous term, which is n minus 1, times n minus 2, times n minus 3. And you can see that this would continue to go along. However, what's key for us here is that we can stop here notation-wise and just say that this is n minus 3 factorial, meaning we would continue to multiply by n minus 4, n minus 5. But all of this is over n minus 3 factorial already. And that gives me a common term that I could, or a common factor that I can then divide out. And that's what we're looking for with these simplifying problems. When we're simplifying factorials, we want to find a common factorial that we can divide out for the numerator and denominator. What's left over is just n plus 1, n minus 1, and then n minus 2. So it would simplify down to those finite set of terms there. All right, let's try number 2. For number 2, we're going to write the formula for the nth term of this particular sequence. We see that it is an infinite sequence, right? This notation here indicating that these terms are going to continue. So what we want to do is we want to come up with the nth term. In other words, we want to come up with what we think the function actually is. So we're going to say a sub n is equal to, and we got to come up with this here. Now, this can be tricky in a lot of ways because there's really no one-size-fits-all type of rule or approach to this. One thing that I would encourage you to try to do is to write the n values right above each of these terms, just so we can kind of see, all right, do we see some type of relationship between our n values and our outputs? In other words, can we see what's happening to n to give us our a sub n? Well, I noticed that in our numerator, we're taking all of those n values and we're adding 2 to them. So in our numerator, I can say n plus 2, right? Because 1 plus 2 is 3, 2 plus 2 is 4, 3 plus 2 is 5. Now in the denominator, we can see that these are all powers of 5. Specifically, that first denominator 5 is 5 to the first power. That second denominator is 5 to the second power. And so we can see here that these n values are simply the degrees of our bases here. So 5 to the n power. And the final thing that I want to highlight here is that we notice that our signs are alternating, right? We go from negative to positive back to negative. So here we would just want to write that this is negative 1 to the n power. And just check to make sure that that indeed works. When n is equal to 1, we have a negative first term. So there's our a sub n rule. All right. Now let's look at number 3 here. Number 3 is pretty simple, straightforward, plug and chug, right? We're just saying, all right, here's our a sub n rule. This is our lower bound, or letting us know where we're starting, from what n value we're starting, and where we want to finish. Now, we're not going to write an infinite number of terms. The problem is simply asking us to find the first 3 terms. So we're just plugging and chugging. So the first one, when n is equal to 1, we've got 1 factorial minus 1. There's our first term. And I'll simplify all these in a second. Our next term would then be 2 factorial minus 2. And our last term would be 3 factorial minus, oh, excuse me, not 2. This was minus 1. I apologize. It's not minus n, it's minus 1. So this is minus 1. And just to clean this up a little bit, 1 factorial minus 1 is just going to be 0. 2 factorial, which is 2, minus 1 is 1. And 3 factorial minus 1, that's 3 times 2 times 1, which is 6 minus 1. This is going to give us 5. Okay? All right, let's do a little bit of work in our calculators here. And for this next part, I can't show you my calculator right now, but if you turn on your calculator and you hit the mode button, and in the 5th row where it's currently set on function, if you move that over to sequence, what that will then do is allow you to enter in these a sub n rules as a sequence. And you don't honestly have to do this. You could just do this by plugging in these functions into your calculators and just kind of getting a sense numerically of what's happening here. But that is just giving you a quick heads up. So I'll just write that. So that's mode, and then from the function where it's currently set, we want to change function, and you want to change that to sequence. And then you'll know you did this successfully when you're able to, where the y equals screen then becomes the u sub n screen that you see there, okay? And again, you don't have to do this. You could just enter in these functions as they are and just start looking at what's happening with these values. So, and if you even needed to, you could even just put these functions into Desmos right now and just look at their graphs and start thinking about, all right, as n increases towards infinity, what is going on there? What are these outputs doing? And we would see here that for this first one, as we start plugging in larger and larger values of n, this starts to get closer and closer to 1/2, right? And this thought process, the way we're thinking about this, is no different than what we do with limits, right? We're looking at what is happening here as we get closer. If I ask you to find the limit as n approaches infinity of 3n over 1 plus 6n, you can see pretty clearly that this should just get closer and closer to 1/2, right? So let's look at the rest of these And you can go ahead and pause this video and try these on your own. But you should see here that this one would get closer and closer to 2. These terms would get closer and closer to 2. And this one would be unbounded. This doesn't seem to ever settle in on a specific value. All right. Okay. And in these last problems here, again, we're just evaluating these terms. So you should get a sub 3, since we already know the first two terms is 1 and 4. A sub 3 is going to be that term, a sub 3, minus its previous term. So in other words, oh, excuse me, no, it's a sub n plus 1 is the previous term minus that previous term. In other words, a sub 3 is a sub 2 minus a sub 1, which in this case is 4 minus 1, which is 3. A sub 4 then would be, in this case, 3 minus 4, which is negative 1. And a sub 5 would be negative 1 minus that previous term, which would be negative 4. And for this last one here, we're going to say a sub 1 is, we're just plugging in what we know. This is x to the 1, and so this is going to be x. A sub 2 is 1 over 2 factorial, because my n is now 2, x squared. So that's just x squared over 2. And then just for the sake of time, since you see where this is going, you should get the following. Okay? And in the next video, we'll then talk about sequences that either converge or diverge.